Checking design rule violations, DRVs, in VLSI designs, showing the question. Ensuring a design adheres to the defined manufacturing rules is crucial for a successful VLSI fabrication process. Here's how to check for design rule violations, DRVs, in your design. 1. Design rule checking, DRC, tools. Industry standard tools. Most electronic design automation, EDA, tools offer built-in DRC functionality or integrate seamlessly with dedicated DRC tools like Calibre from Cadence or Assura from Siemens EDA. Design rule file, DRF. The DRC tool relies on a design rule file, DRF, that defines the specific layout rules for the chosen fabrication technology. This file details allowed spacing between objects, minimum feature sizes, wire rules, and other critical parameters. DRC execution. Once the design layout and DRF are loaded into the DRC tool, the tool performs a comprehensive check of the entire layout, comparing it against the defined rules. 2. Types of DRC checks. Spacing rules. DRC verifies if the spacing between different objects, metal lines, vias, transistors, meets the minimum allowed distance specified in the DRF. Insufficient spacing can lead to electrical shorts during fabrication. Width and size rules. The tool checks if the width of metal lines, polysilicon gates, and other features meets the minimum and maximum allowed dimensions. Deviations from these rules can impact signal integrity or device performance. Layer stack-up rules. DRC ensures proper placement and layering of different design elements, metal layers, vias, diffusion regions, as defined in the technology's layer stack-up. Well and contact rules. Checks related to placement and sizing of well regions and transistor contacts are performed based on the DRF specifications. 3. DRC results and analysis. Violation reports. The DRC tool generates detailed reports that list all identified violations. These reports categorize violations based on type, e.g., spacing, width, and location in the layout. Visualization. DRC tools often provide visual aids to highlight locations of violations directly on the layout, making it easier for designers to identify and fix the issues. 4. Addressing DRVs. Layout modification. Based on the DRC reports and visualization, designers need to modify the layout to eliminate the violations. This might involve adjusting spacing, rerouting signals, or resizing features to comply with the design rules. Iterative process. The DRC process is often iterative. After fixing a set of violations, the design is rerun through DRC to ensure no new violations are introduced and all existing ones are resolved. 5. Additional considerations. Electrical rule checking, ERC. In addition to DRC, some EDA tools offer electrical rule checking, ERC, that verifies potential electrical issues like high current densities or unexpected voltage drops. Layout vs schematic, LVS, verification. Layout vs schematic, LVS, verification ensures the physical layout accurately reflects the intended functionality specified in the schematic diagram. Conclusion. Effective DRC checking is an essential step in the VLSI design flow. By utilizing robust DRC tools, designers can identify and address potential layout issues that could lead to fabrication problems or malfunctioning circuits. This helps ensure successful chip fabrication and reliable operation of the designed VLSI circuit. Checking for timing design rule violations, DRVs, in VLSI designs, showing the question. In VLSI design, ensuring your circuit meets not only layout rules but also timing requirements is crucial. Here's how to check for timing DRVs. Understanding timing DRVs. Distinction from layout DRVs. Timing DRVs differ from the layout DRVs discussed previously. While layout DRVs focus on physical layout adherence to fabrication rules, timing DRVs ensure the circuit operates within specified timing constraints. Metrics and violations. Timing DRVs typically involve exceeding maximum transition times, max_tran, exceeding maximum capacitance, max_cap, or violating setup and hold times for flip-flops, registers. Identifying timing DRVs. Static timing analysis, STA, tools. Dedicated STA tools, like Synopsys PrimeTime or Cadence Tempus, are used to analyze the timing behavior of the design. These tools consider factors like cell delays, net capacitances, clock skew, and operating conditions. STA reports. The STA tool generates reports highlighting potential timing violations. These reports detail the specific nets or paths exceeding timing constraints and the associated slack values, difference between available time and required time. Addressing timing DRVs. Cell sizing optimization. Adjusting the sizes of standard cells along critical paths can reduce their delays, improving overall timing slack. Larger cells often have lower resistances, leading to faster signal propagation. Clock tree optimization. Techniques like buffer insertion or strategically placed clock trees can help minimize clock skew and ensure a more uniform arrival time of the clock signal at flip-flops. Logic optimization. Techniques like logic restructuring, rebalancing fan-out, or pipelining can potentially reduce the number of logic levels in critical paths, leading to faster signal propagation. Design constraints tuning. In some cases, relaxing non-critical timing constraints might be possible, providing additional leeway for meeting critical path requirements. However, this should be done with caution to ensure overall circuit performance is not significantly impacted. Iterative process. Similar to layout DRC, addressing timing DRVs is often an iterative process. After implementing a potential fix, the design is rerun through ASTA to verify if the violation is resolved and identify any new violations that might have been introduced. Additional considerations. Library characterization. Timing libraries, containing cell delays and other timing characteristics for standard cells, are crucial for accurate ASTA analysis. Ensure these libraries are up to date and represent the actual cells used in your design. Corner cases and private variations. ASTA analysis should consider variations in process, voltage, and temperature, private, to ensure timing margins are sufficient across different operating conditions. Conclusion. Checking for timing DRVs through ASTA tools is vital for ensuring your VLSI design meets its performance goals. By analyzing timing reports, implementing appropriate optimization strategies, and iteratively refining the design, you can achieve a circuit that operates reliably within specified timing constraints.